Hello and welcome back to my channel. Palindromes. A palindrome is a number such as 24242 because it reads the same forwards and backwards. My colleague claims that all palindromes with 4 digits are divisible by 11. Is this true? So first, in order to get ourselves thinking about this, we need to start writing down a few questions. First, we can at least find palindromes with 4 digits. That's our first task, to find some palindromes with 4 digits. And then we want to find out whether the claim is true. Is this claim true? And to do that, we'll have to test. But we want to also find out what's required in order to determine whether this claim is true. Now, these are our questions again written here. We need to find some 4-digit palindromes. We need to determine whether the claim is true. And in doing so, we need to also find out what is required. So the first thing we want to do is to specialize, of course. We can look at some 4-digit palindromes, such as 2112, 3003. These are some that I've just at random chose. 5775. You could have chosen a different list of palindromes, but first just specialize with random palindromes, 4-digit palindromes. Now, what do I want to show? And the answer to that is that I want to find or show that out of all the palindromes, out of all 4-digit palindromes, they're divisible by 11. So I want to find all 4-digit palindromes that are divisible by 11. Or to even answer the question further, whether all of them that I find, or all of them, all 4-digit palindromes, are divisible by 11. So I just made a mistake. I want to find if, I should be saying, if all 4-digit palindromes are divisible by 11. That's the task. We want to know if all of them are divisible by 11. So I've tried several specific examples. I tried several specific examples. and the result seems plausible. But I can't be sure about this. And even though I've specialized with specific examples, I can't be sure that my result is always correct just by specializing. Another thing is that we don't want to actually test every 4-digit palindrome. That could take us a while. In fact, there are actually 90 of them. So we want to find a better way. And one of the things we can do is to determine whether there's some underlying pattern that we can actually identify. And then we can actually make some progress from that stage. So we need to get an idea of the underlying pattern. And then we'll see where we go from there. So these are my 4 cases that I tried. 1,221 divided by 11 to get 111, and 3,003 to get 273, 6,996 to get 636, and 7,557 to get 687. So each one of these have been each one is divisible by 11, and so that shows that the claim is partly correct, but I can't see any pattern from this. And now I need to review how I've used specialize in here and what I've discovered. So for my 4 cases, I've concluded that there's no obvious pattern. Even though choosing examples at random is a good way of specializing and gives me an idea of what's involved. In searching for patterns, I can only actually make progress if I do this specializing in a systematic way. So my 4 cases were just 4 cases of random numbers, random 4-digit palindromes. But the next stage, I need to become systematic towards my choice of palindromes and to test those. So I want to become systematic in specializing. With the hope of being able to identify the underlying pattern. So how do I conduct systematic specializing? A few questions pops up. What is the smallest 4-digit palindrome? What is the next smallest? What is the next smallest. Can a palindrome be changed to form another palindrome? Can a palindrome be changed to form another palindrome? For a start, we can be systematic by starting with the smallest palindrome, and then we can work up in ascending numerical order. So we have the first palindrome, 4-digit palindrome, is 1001. The next, and so on. And when we conduct a check, we've divided each of these by 11. So the first one divisible by 11, it gives us 91. The second divided by 11 gives us 101. This one is 111. And this one 121. So all of these divided by, or each of these, sorry, I should say, each of these divided by 11 gives us the result here in this row, which shows and supports the claim made by my colleague, but it suggests a bit more, and I'll look deeper into this to see what's the underlying pattern. Right, a few observations about the 4 cases of systematic specializing here. We can see from the palindromes, they're increasing by 110 each time. So from 1001 to 1111, it's an increase of 110 and so on. The quotients are rising by 10 each time. So we're talking about the result here of division by 11. It's an increase of 10 each time. So we have a bit of support for the claim made by my colleague that for all 4 digit palindromes are divisible by 11. But we need to look deeper into this. We can see that the difference between successive palindromes is 110. So the difference between palindromes is 110. And the palindromes, the quotient is an increase in a difference of 10 from between each of the quotients. Difference of 10 between each quotients. So we have 2 things. We have all the palindromes which we've chosen here are divisible by 11. And also, the difference between palindromes, which is 110, is also divisible by 11. Now, since all the palindromes are obtained from 1001, which we started with here, and by adding 110, then all palindromes must be divisible by 11. Now, so far, this resolution covers all the cases, or does it? Cover all the cases I used. If all palindromes could be constructed by successively adding 110 to 1001, then they will all have 1 as the unit digit. But this is not actually true. All we've considered here is palindromes with the first digit being 1. For example, if we looked at a palindrome 7557, we have 7 as its unit digit. So my resolution here does not actually hold for all palindromes. Since this example here, 7557, violates the pattern mentioned earlier, above here. So specializing can help to identify the weakness in our resolution. And that's exactly what has happened now. We need to look a bit further into this. Right, so we've done a bit more specializing here. I've constructed this table of palindromes and their differences. And here are the observations. We have the successive palindromes differ by 110. We've established that early on. But when the 1000 digit changes, the difference is 11. Here's an example. We have a change from the 1000 unit being 1 here to 2. The difference is 11. Providing the 1000 units are the same, the difference is 110. We need to find a general reason why this pattern is valid, or general reasons for that matter of fact. Now, first, we have that successive palindromes with the same thousands unit must have the same thousands unit to be palindromes. For example, 2002 here and 2112. We also note there's a difference in the second and third digits. There's a difference between the second and the third digits of 1. The difference between the palindromes is 110. There is a difference in the second and third digits. That difference of 1. Okay, so for this to hold that true, this claim that there's a difference of 110 between successive palindromes, if you look at the second and third digits, the difference here is 1. Between 8 and 9 is 1, and also 8 and 9 here. So wherever we have this difference, successive difference of 110, there is this difference between the second and third digits of 1 between successive palindromes. Our next observation is that successive palindromes with a different 1,000 units are calculated by adding 1001. Are calculated by adding 1000, 1001. For example, we have 1881 add 1001, which gives us 1991. Now, if we want to reduce the second and third digits, we subtract 990. To reduce second and third digits, we subtract 990. Here's an example. 2 examples. We have 1991 minus 990 gives us 192. But then we have something slightly different here. When we start with the first palindrome, 4-digit palindrome, and we subtract 990, we get a difference of 11. So in all cases, the differences are divisible by 11. That's one conclusion we can make. At this point, I'd like to review how I've used specializing in finding a solution or a resolution to this problem. All right, let's review this. We need to find or review the different ways I've used specializing here to find a resolution. First, it's helped me to understand the question. To help me understand by making me clarify the idea of a palindrome. It's allowed me to discover the form of a 4-digit palindrome. Let's go. It allowed me to convince myself that my colleague's claim was likely to be true. I've also used it for testing whether the pattern was correct. So as you can see here, that specializing can be used quite effectively in many ways, which makes it fundamental to mathematical thinking. Some more observations. Every 4-digit palindrome has the shape A, B, B, A. A and B represent digits. A and B represents digits. And has the value 1001 A. Which we can write as with a bit of factorization. I urge you to go through this and to convince yourself that my algebra is correct. And this gives us 1001A and 110B. And further to this, we can identify a common factor of 11. Oops, play that nicely. And then we can factorize this yet again to this. So this is our general form of a 4-digit palindrome. We have 11 brackets 91A add 10B. And this leads us to another aspect of mathematical thinking called generalization or generalizing. Now, generalizations are essential in mathematics. In all of mathematics. Specific results are quite useful, but mathematical results are always presented as a general case. And there are two aspects of generalization or generalizing. One is being systematic in specializing. Which is a necessary activity to aid generalizing. The next aspect is we need to be cautious about believing an observed pattern or generalization. And if you go through this video again, you'd see that that was the case when I first came across the initial pattern that all 4 digits palindromes were divisible by 11. Only to discover as I looked further or deeper into specializing, or by specializing that, there is a lot more to it. We also need to test with a wide variety of examples. So to be cautious, we should go about testing across a wide variety of examples. Before I end this video, just a few points about writing notes. You should record your experiences. So they don't get actually lost. So, not to lose them, and so that they can be analysed and studied later. This helps to notice your experiences, become aware of them, and it contributes to mathematical thinking. And that brings us to the end of this example on palindromes, and giving you an idea of what's involved in most of the polished examples or solutions you might see in a textbook, regardless of whether it's secondary school mathematics graduate or undergraduate. Thanks for watching this video. My name is Alistair. If you like this video, give me a thumbs up and please subscribe to my channel. Bye for now.